Hello, everyone. Today we're going to be talking about when can you remove a resistor from a circuit. And you can only do this when, assuming there's current flowing in a circuit, then you have to look out for two things. You have to look out for when a resistor is in series with an open circuit and when a resistor is in parallel to a wire. Before we do examples of this, I want to review some prior knowledge. But first, when do we see this? We often see these scenarios of removing a resistor when you're solving for three items: voltage and current. This is often seen when you're solving for Thevenin, the short circuit current, also known as Norton current, and when you're achieving or completing linearity superposition. And then third, when you're solving for equivalent resistance. An example of this is our Thevenin. So before we do examples, let's do some review. Let's make sure we're all on the same page and we all have the same prior knowledge. So we have this circuit shown below. We have a resistor in parallel to a wire. These three dots on the left-hand side means that this circuit drawn here is some part of a bigger circuit. So I'm assuming you all know that a wire has 0 ohms. A wire is equivalent to a resistor with 0 ohms because you use wires to assume that there's no voltage drop. That's how you create a circuit, right? A wire is theoretically has no resistance across it. That's how you're able to connect things without dropping any voltage. So technically speaking, to simplify this, I can redraw it as, let's try to stick with one color, a resistor in parallel to another resistor. And it's 0 ohms because a wire has 0 ohms across it. And mathematically, the equivalent resistance then would be 1 over Rx plus 1 over 0. Or you can say Rx times 0 divided by Rx plus 0. No matter how you want to see it, anything times 0 is 0. So R equivalent becomes 0 ohms. What has 0 ohms across it? A wire. So nonetheless, this becomes just a wire. So we've shown that whenever you have a resistor in parallel to a wire, you can get rid of the resistor. This is just using mathematics and the concepts of components being in parallel. Now, if you want to go back to your physics or physics 2 or physics AP class, you may have heard that this Rx is being shorted because there's a wire in parallel to it. This is referring to current. So the way conventional current, positive charge movement, is that current would come from this part of the circuit and it has to split. So current comes and splits to this and this. Now, this current here, let's call it IZ. IZ has no resistance in that path. So this current here called IS, all of IS is going to go through the wire. So that means IS is equal to IZ. Why is this the case, Mr. C? Because current travels through the path with least resistance, or if it exists, the path with no resistance. Theoretically, a wire has no resistance, so Rx is ignored. You can remove Rx. Or if you use mathematics, you can see mathematically we can redraw this without the resistor. Thus, a point proven that you can remove a resistor when you have a resistor in parallel to a wire, whether you go by the physics of the current, the conventional current, or you go by mathematics. I prefer to go by math. So now let's simplify this case. You have a resistor in series to an open circuit. I'm hoping we all are on the same page that note an open circuit has infinity ohms of resistance. You can look it up in the textbooks. In the textbook, I'm not going to try to derive it here in this video. I'm trying to make this quick, but from point A to point B, if you have nothing in between but air, then that's an open circuit, and that's infinity ohms. So if you have a resistor Rx in series to infinity ohms, mathematically you're doing Rx plus infinity ohms, which is equal to infinity ohms, which means that this can be redrawn as an open circuit. And therefore, the second point proven, that if you have a resistor in series to an open circuit, you can redraw this part of the circuit as simply just an open circuit, and you've removed Rx. So with these two fundamental building blocks, we're now going to see other those scenarios that I mentioned earlier. Solving for voltage, solving for current, often see with Thevenin and ISC and linearity superposition, and then solving for equivalent resistance, often seen with R-Thevenin. So let's do Thevenin first. If we're solving for Thevenin, the assumption that a voltage exists means that there is current flowing. And like I mentioned first, if there's current flowing, you have to be careful if scenarios, resistors in series with an open circuit or resistor in parallel with a wire. So where is this current that's moving? It's coming from the battery. If you follow conventional current, current will go here, then split again, but does current actually go through R5? Some students may say, it will, and then it'll go backward because there's nowhere else to go. No, no, no. Current is either going counterclockwise or clockwise. If you claim it's counterclockwise and your math ends up being a negative number, that just means your assumption was wrong and it's going the other way, right? We're in 2024, so that's not something new. So you assume that current's going in this direction, but you can never assume that current just changes its direction in the wind. That doesn't exist. So you can't say current's going here, oh, it can't go anywhere, so it goes backwards. No, current can't go anywhere. Another way you could think about it is for my the people who learn by uh, with movement or with touch. If you had R5, a legit resistor, in your breadboard, only one end of it is connected to the rest of your circuit. The other part is connecting to midair. So where does the current go? Just up to the ceiling or nowhere? So you can pluck R5 off the circuit board. Or you can go back to math and notice that if you zoom in, R5 is in series with an open circuit. And because we assume current is moving, and we see that R5 is in series to an open circuit, we can remove R5. So we can remove R5 because in series with, I'm going to put OC, open circuit, between nodes A and B. So if you were to do this problem, then you would remove R5, and now your new circuit is, one second, you remove R5, or as shown earlier, it's just an open circuit, right? So technically speaking, we just have this now. It's still just an open circuit from here to here. This path is what has R5 and the open circuit in series. We proved that you can remove R5. I've done that. If you look here, it's just an open circuit. So nothing illegal. Now, putting that Thevenin is still here, here's R4. Now your task is to note that Thevenin is equal to VR4. So you would use whatever circuit analysis that fits this solution to find the voltage across R4, because that is equal to Thevenin. Remember, things in parallel share the same voltage. Okay, so we have shown an example where solving for Thevenin, you may possibly have to remove a resistor. And that's because R5, as mentioned, R5 was in series to the open circuit across nodes A and B. Cool. Now, what happens if you're solving for ISC? If you're solving for ISC, then that means you need to draw the current going from A down to B. Bonnie Ferry often has an arrow drawn here. Now, you have drawn a wire from A to B. What did you just do to R4? If you look and zoom in here, you have shorted R4. Synonymously, R4 is in parallel to a wire. What is the equivalent resistance in the circled blue ink region? Just a wire. We proved that earlier. So that means you can remove R4, comma, after placing wire between nodes A and B because R4 is parallel to wire. Peace. So how do I redraw my circuits? You would have the voltage source, the resistor, ground, this resistor, and only the wire. And this current going through this wire is your ISC, which is also equal to IN. So another example where you can remove the resistor. And it's not that you just can because, you know, you have the right to. You have to have some type of mathematical proof or physics principle that supports this. And we have already demonstrated using math and the concept of conventional current to show that R4 in parallel to a wire simplifies to just a wire. Cool. Now, let's see an example if you're going to utilize linearity and superposition. So, solve for VR3 due to Vs. If I'm solving VR3 due to Vs, I have to zero out all of my other sources except Vs. So, that means, just going to write step 1 here, zero out Is. So I now have the battery and R1 and R2, and I have my open circuit because that's how you zero out Is. Then I have my resistor. Then I have my resistor here. And what happens to R4? Let's zoom in. R4 is in series to an open circuit. What can you redraw this part of the circuit if you have a resistor in series to an open circuit? An open circuit. We've shown that earlier. You could go back in the video. So now this circuit can be redrawn as, if you think about it, I could have drawn an open circuit across here. But there's no need. Think about if you had a proto board. This would be a wire right here. This would be a wire. It's just going to midair. You have a wire and a wire going to midair. There's no interaction going on. So technically, you could redraw it as this. And then using circuit analysis, solve for VR3, which is not the focus of this video. But I've shown yet another example where you may want to use linearity and superposition, and you have had the opportunity to remove a resistor. Why? To zero out the current source, my circuit now becomes R4 in series to an open circuit. And if they're in series, I could redraw that as an open circuit, which I've done here. Another example with linearity and superposition. Solve for VR3 due to Is. So I have to zero out now my voltage source. So how do I do that? My voltage source becomes a wire. By zeroing out my voltage source, what did you do here? You shorted this resistor, which was R1. R1 is in parallel to a wire. What can you redraw that part of the circuit? You could redraw it as a wire, shown earlier in the video. So you've removed a resistor, which means this circuit is now equal to current source, the resistor, a wire, the resistor, oops, the resistor, wire, resistor, and plus 1, VR3. Look at this problem. This is quite interesting. What do you notice about this wire and this resistor? They're in parallel to each other. They have the same common top and the same common bottom node. So you can replace R3 as a wire, which means it has no voltage across it. So this circuit actually is none other than R3 not in circuit, therefore VR3 due to IS is equal to 0 volts. It wasn't the focus of my video, but thought I'd show you that. Now, what about solving for R Thevenin between nodes A and B? It was a great example. This is something that could, I don't know, show up on your exam or you've seen in homework. So, when R Thevenin, what do you have to do? What's the first thing you have to do? You have to zero out your sources. Let's bring this up a little bit. Now, if I zero out my sources, my voltage source becomes a wire. My current source becomes an open circuit. What happens here? And what happens here? I have the opportunity to remove two resistors. Here because the resistors are parallel to a wire. Here because the resistor is in series to an open circuit. But Mr. C, there's no current flowing through in this circuit. False. Very false. To explain this, I'd like to take a break and show you something, or explain something. In Lab 1, we asked you to use your MIDAC to measure the resistance of a resistor. So you had a resistor, right? It looked something like this. It had color bands, and it had a wire on the left and a wire on the right, correct? So you took your red and black leads, and then you had them connected to your MIDAC. MIDAC, right? How do you measure the resistance? Well, current is leaving the MIDAC. It's leaving from the positive terminal, going down the resistor, and coming back through the black lead, because the black lead is like a negative terminal and the red lead is like a positive terminal. So current is going from red to black, and I have a resistance across my resistor. So the MIDAC has a test current, let's call this I test, that flows through your resistor, and the MIDAC's therefore measuring voltage. That's why when you measured resistance, you left the red lead on the voltage side, right? You didn't switch it to current, you left it on the voltage because the MIDAC is sending a test current through the red lead into your resistor and then back to the black lead, and it's measuring voltage. How? Using Ohm's law. It's going to do current times whatever the resistance is and give you voltage. That's how it's measuring the voltage. And that's how it tells you, here's the resistance value, because it does the math. So when you're doing R equivalent, you're finding your R Thevenin. When an instructor says there's no current moving through the circuit, there's no current, parenthesis, from sources moving in the circuit. But there is current coming from the MIDAC. You see? What we're not explaining is that there is a MIDAC, quote unquote, being used and sending current to your circuit, and it's going to come back. Mr. C, where is it sending current to? To node A. That's why it's usually associated with a positive sign. But Mr. C, where's the current going back to the MIDAC, this theoretical imaginary MIDAC? From the negative terminal. That's why the B has a negative terminal. When we ask you to find R Thevenin, you're really trying to find the resistance of the circuit that a MIDAC would measure if you zeroed out your sources or turned off your voltage source and turned off your current source. So my whole premise that scenarios where you may need to remove a resistor, what was the fundamental premise? When current flows in a circuit. And I am stating here that when you're solving for, where is it? R Thevenin of a circuit, there is current, but it's not current from the current source. It's not current from the voltage source. It's current from the MIDAC that you would have been using to measure the equivalent resistance, known as R Thevenin, of the circuit. That is why I care about this resistor in parallel to the wire, and I care about this resistor in series to the open circuit. So if you had to simplify your circuit, one second, because I need to move stuff around. And I don't have time to do post edits of my YouTube video. So, to simplify your circuit, now you have, well, this is a wire in parallel to resistor, so it's a wire. Wrong ink. All right. Then you have a resistor. Now I have a open circuit in series to resistor. That's just an open circuit, so I'm going to leave it B. Here's my other resistor. Here's my other resistor. A, B. And now you're finding your R Thevenin. You would continue simplifying this circuit. So this is then R2, this was R2, this was R3, this was R5. R2 and R3 are parallel to each other. If you don't believe me, notice that they come from this node and this node. So they have a common bottom and another common top node. So that means I have R2 parallel to R3. And then here's my R5. And what do I notice about these two resistors? They're in series. So this means that now I have R5 plus, in parentheses, plus R3 parallel to R2. This thing right here is your R Thevenin. Why? Because if we go back to this example, you just simplified your circuit to the resistor that you're going to measure with your MIDAC. Look, you could put your red lead here, because this was where A was, this was where B was, minus, plus. You could put your red lead here. You can put your black lead here. It's going to go to the MIDAC. MIDAC. See? So, when an instructor says, when you're solving for R Thevenin, there's no current from the current source, there's no current from the voltage source, there's only current from the MIDAC. Perhaps instructors should improve how they're speaking so that there's more transparency and explicit explanation, myself included. So, these are the scenarios where you may remove a resistor. If there's current moving, you have to see, when do you meet these two conditions listed here? When a resistor is in series with an open circuit and when a resistor is in parallel to a wire. Now, when can you not remove a resistor? Well, what about this following question? What about when, who wrote this? I did. What about when, what about when simplifying a circuit to a Thevenin equivalent circuit? Okay, let me explain something. If you're simplifying a circuit, is there current moving? It depends. If you're solving for voltage or current, then there's current moving. So yes. But when you're simplifying a circuit to its Thevenin equivalent circuit, okay, I want to explain that this open circuit here is not an open circuit. I know it looks like an open circuit. I know that's what I just called it, but it's not an open circuit. It is a region that we are simplifying a circuit with respect to. That's what it is. If you ask me how tall I am, on a good day with good posture, I'm 5'8", with respect to the ground that we're standing on. If we're standing on Mount Everest, I'm still 5'8". If we're standing at a beach, I'm still 5'8". But if you ask me how tall are you with respect to the bottom of the ocean, now I have a bit more pride and I'm no longer 5'8", right? So if you're simplifying a circuit, it's with respect to whom? With respect to what? From where? That's the thing that I think the instructors need to improve their explanation a bit better. If you're trying to simplify a circuit to Thevenin equivalent circuit, you're doing it from the open circuit, assuming we were solving for voltage or current. That's why I'm using the word open circuit. So if we're going to simplify this thing, I'm simplifying it from the point of view of the space between node A and node B. Now, if I'm doing that, then from here to here to here, then I'm not seeing an open circuit or a wire in parallel to a resistor. Unless the creator of the homework problem did that on purpose, which wouldn't make sense. But I want to just claim that if your gut feeling is, oh, R5 is in series to the open circuit. No. We're not solving for voltage. We're trying to find the Thevenin equivalent circuit. It's an equivalent circuit from a point of view. Whose point of view? This space between node A and node B. So R5 stays there. And you simplify the circuit, which is not the point of this video, but if you were to begin it, you would notice, again, your goal would be to go from here to here. Do you notice that there's an open circuit here? Whoever created the Thevenin equivalent circuit, they didn't say, oh shoot, our Thevenin is in series our Thevenin is in series to this open circuit. Remove it. No. There's a reason why they want to draw it like this. I explain to my students in my sections, it's like creating a robotics arm. If you create a robot arm, that's your team, just the arm, you're going to have to attach it to the rest of the robot. I need to know how much voltage is across the open part of your circuitry that's going to connect to my part, which is the shoulder, right? So that's V Thevenin. That's the voltage across the open circuit. But to do that, I need to design the whole arm first. I want to simplify it to just this. If you immediately just canceled R Thevenin, I don't know the R Thevenin of my arm anymore, of the robot arm. So this is when you cannot remove a resistor. You cannot remove a resistor when you're simplifying a circuit to a Thevenin equivalent circuit. Similarly, you cannot remove a circuit when you're solving for the Norton equivalent circuit. This is a Norton equivalent circuit. Notice that there's this space between nodes A and B. Why didn't the inventor of Norton equivalent circuit remove Rn? Rn is in series to this open circuit, Mr. C, so I should remove it. No. There's a reason why it's not there. It's because sometimes in engineering life, electrical engineering life, you want to know what this circuit can be simplified to with respect to a Norton equivalent circuit. Why would that ever be the case? If I have a robot arm and it has a battery in it, it could send current to the rest of the robot when it's attached to the rest of the robot. You and your engineering colleagues create a robot arm. If current is going to come out of this robot arm, how much is it? What's the maximum current that could come out? That's IN. What's the resistance of your arm? That's the Norton resistance. Please note, Rn is equal to R Thevenin, and In is equal to ISC. So, when can you not remove a resistor? When you're simplifying a circuit to the Norton equivalent circuit, when you're simplifying a circuit to its Thevenin equivalent circuit. Any other time, if there's current moving, and if you are in either of these two conditions, you can remove the resistor. And again, remove means that you have mathematically demonstrated, or you have demonstrated with the physics principles, that the resistance doesn't exist when you simplify the circuit because current is moving. Okay, I hope that explained it better. I'm not sure how long this video is, but I tried to explain it as efficiently as possible in a short amount of time. All right, short amount of time notice to make this video. All right, thank you for your time. If you have any questions, email me. All right, that's all.